Yeah, there was some issue. We can start now. Okay. Okay. Yeah, now it is fine. Great. Okay. Okay, yeah, let's start. Sorry for the wait, guys. Okay, yeah. So anyone would want to tell me what is heap? Let's start the class. Okay. Anyone wants to explain what is heap? Anyone, whatever you know about
Yes,
heap,
sir.
you can explain me.
Yes, sir. EP is an.
Whatever you guys know,
Hello.
it's okay.
Am I audible, sir?
I don't want key; it should be perfect. What do you know
Hello.
about heap? Anyone?
Hello. Am I audible? Hello.
No one wants to speak.
So it's basically a tree-based structure, in that it has like a complete binary tree in which like all the levels are filled except the lowest level, and all the elements are towards the left.
Great. Anyone else?
Hello. Am I audible, sir?
Yeah, you're audible now.
Yes, sir. It's a special type of tree-based data structure in which a tree is a complete binary tree. Means complete binary tree means every level should be filled unless last level. In last level, every element should be as left as possible in complete binary tree.
Agree. Agree. Anyone else? No one knows it. Only 2%. Okay, I'll tell you what it is. Okay, a heap is a binary tree. Okay, a special kind of binary tree in which the root element, okay, this root element will always be greater than all its childs. Okay, so this is the root element. Let's say it has two child. It has, okay, it has some more child. It can have some more child like that. Let's say it has some more child like this. Okay, so this element will be larger than all the children. Okay, all the children. There are how many children for this element? 1 2 3 4 5 6 7 8. So there are, this element will be larger than all the element in a subtree. Okay, so for this the subtree is these five elements, and these three elements, right? So total there are 8 more elements other than this. So this element will be larger than all the other elements below them. Okay, so this element, let's say whatever it is, it will be larger than all the elements below it. So if we want to make a valid heap, it will be like, let's say we make here 10, then we make here, let's say 9, we make here, let's say 7, we make here, let's say okay, let's make it 5, let's make it 8. Okay, let's make it 4, let's make it 5. Okay, so can you see this is all satisfying that condition? Let me just complete it. So this is 10, right? So how many elements are below 10? Anyone wants to tell? They are this element, this element. They're actually 1 2 3 4 5 7 10 elements, 8 elements, right?
Elements.
Yeah, so this all 8 elements, 3 4 5 8 4 5, these all are smaller than 10, right? No other element are more than 10. So whatever element are below 10, that will be less than it. Okay, that is the a simple definition of heap. And it should be true for all the nodes, not only for root. It should be true for all the nodes. So if we come here for 9, if you can see, for 9 also, all the elements which are below 9 are smaller than them, right? 5 8 3 4, they all are smaller than them. Agree with me, guys?
Yes, sir. Sir, but in Geeks for Geeks, I means before class I read some theory concept on it. They given max heap and min heap. In max heap, the first root node should be maximum, then all
Mhm.
the child. But
Right.
in mini,
Hmm.
the root node should be minimum, right?
Right. Exactly.
Uh,
Exactly. So there are two kinds of heap, right? So first of all, we are declaring the max heap. Then we'll go to min heap.
okay, sir.
Okay. Yeah. This is a max heap. Okay. Now when I would when I'll tell you min heap, then I'll tell you what is there are two types of heap: man heap, max heap, and min heap. But right now we want to discuss what is max heap. Okay. Now, so this element, this root will be actually larger than all the children's. This is agree. Like you guys agree with this?
Yes, sir.
There will be no other element greater than 10 below 10. Okay. That is the simple rule. And this will be true for all the other nodes. Let's say if you go for 9, it will be true for them as well. If we go for 7, it will be true for them as well. Can you see? We have uh, a rule. This element 8, right? This is more than 7, but it is not under 7, right? Can you see? It is under 9. It is not under 7. So whatever elements are below 7, they will be actually less than this. Okay. Similarly, for this 5 also, there are only 2 elements. They both are less than it. For it also, there are no elements. So yeah, but it is a basic condition which shows ki, uh, like all the whatever node is there, that will be larger and that will be maximum if we if we see in this subtree. Let's say this is a subtree, so the root will be maximum for all subtrees. The root will be maximum for this subtree. Again, the root will be maximum. Okay, for this subtree, the whole subtree, this root is maximum, right? So whatever subtree you take, the root will be the largest element. This is a simple case. Okay, this you agree, guys? Great. One more thing here. You might be thinking that let's say we have another element 10. Let's say, if we go like this, if we just erase it, can we put here 10? Anyone wants to answer it? Can we put here 10? You can add in chat box. No, right? Anyone? So where it will go? If a 10 comes, where it will go? Where should we place it then? If equal elements come, it is not a hash set or set, right? Where we cannot have same elements more than one. We can have same elements, right? So 10 can have, we can have more than one instance of a same element. So where it should go? Left node of 8. Here it should go like this. Just below the level of root. So it is below the level of root only. Why it is not possible then? I'm asking now. You guys are saying it is not possible, but it is below the root of level of 10 only. So what is the issue with it? You don't understand? Because it is overlapping since the same value. Okay. Now, what I told you for each, for each subtree, the root, all the other elements than root should not be more than root, right? They should be less than or equal to root. This element will be the largest. Okay. There will not be any other element more than this 10, but there can be elements which are equal to 10. Okay, so this can be here. Okay, this 10 can be here. It is possible. Okay, we can have more than one instance for one element, so we can have elements, same elements we can have, so that will go to the it will just get attached to the parent. So it's possible. Okay, if we have one more 10 in place of 7, also we can write 10. Here also we can write 10. It's possible. Okay, all the children's can be smaller or equal to root, but they will never be larger than root. Okay, and it will be true for all subtree. For this subtree, okay, for this subtree, okay, for this subtree, this root will not be smaller than any of the child elements. That is the basic rule. Okay, we can have similar elements, but this will be larger or equal to the maximum element which is present below it. It will never be smaller than any element. So yeah, this is a basic concept of heap. Okay, now this heap, whatever we learned just now, okay, the root will always, for each subtree, the root element will always be larger than or equal to the, like, no, it will be there will be no other element below in any subtree. The root will be the largest element. Okay, can you see in this subtree this 10 is the largest element. Now this is called as max heap. Okay, why this is called as max heap? Because in this root is largest, okay, for each subtree. Okay, remember this word subtree. That means it will be true for each node. Okay, which is below, like, no, for each node, whatever subtree that node is making, for that, but for that subtree, that node will be the largest element. This will be true for max heap. Now, anyone have any doubt in max heap now? Cool. Now let's go for min heap. So only there are two kinds of heap: max heap and min heap. Okay, let's go for min heap. Okay, it's exactly just opposite. Okay, there will not be any element smaller than the root element below it. Okay, for any subtree, the root element will be the smallest. That's it. We can have element which is equal to root, or which is more than root, but we'll not have any element which is less than root. Okay, that's just a vice versa, we can say. So let's say we make one here, so it can have two, it can have three, it can have, for each each like, no, subtree, it will be true. So let's say it is like this, 5, like that. Let's say that is not possible here. Let's say we have something like 5 and then we have 4. Okay, can you see it is like, satisfying this condition? For each subtree, the root will be the smallest element. So for this subtree, the smallest element is 1, right? So this is the root. For this subtree, the smallest element is 2, and that is the root. For this subtree, the smallest element is 3, that is the root. For this subtree, the smallest element is 5, right? And that is the root. There can be more than 5, but root will always be the smallest. Okay. Any doubt with min heap? I'll tell you how left child and right child are decided. That is the next step. Where I write 4, yeah, this is actually not 4. This should be 7 actually. Okay. Is it clear now? Cool. Now, let's say we have a, let's make a binary tree, a complete binary tree. Anyone have doubt what is complete binary tree? Anyone? Okay, I'll just quickly tell you what is a complete binary tree. And complete binary tree, the leaf node will always be at the least, like, no, at the last level. Leaf nodes will all be at the same level. Okay, they will not be something like that. Let's say 3, and let's say 4, let's say 5. Okay, and let's say, how should I tell you? Okay. Okay. No, not this way. If I give you an example, stand by this. Anyone wants to tell me, is it a complete binary tree? Question for you guys. No, yes. Yes, it is. Very good. Okay. So let's say if we make one more element here, let's say we make it 7. Now what do you say? Is it a complete binary tree now? Again, a question. This was yes. Okay. Now this one, for this one, what do you say? No. Okay. Yeah, why the chat box is not coming here? That is the issue right now. Is it coming here but not coming there? Why are Mm, okay, let's do like this then. Hmm. Okay, where was we? Huh? It's not a complete binary tree, right? Because we have one leaf node here, we have one leaf node here, and one. Sorry, this is not a leaf node. Definitely. Sorry, my bad. One leaf node here, right? So we have three leaf nodes. Okay. That is not possible. That is not possible. Okay. In complete binary tree, all levels will be filled. The last level will not, like, no, the last level will always be filled up to the left side. Okay. So it will be like, I'll show you. This is first level, this will be filled. This is second level, this will be filled. This is third level, this will always be filled. Okay. Let's say this is the last level. So last level will always be filled only from the left side. It can have, it can be filled till light also, but it will not be like this. Let's say 3 is here, and then let's say we have 7 here. It will never be like this. All the elements will be on left side. Okay. Do you understand what I'm trying to say? All the elements will be on left side. It is not a heap. I'm just telling a complete binary tree. So all the elements will be on left side. Let's say we have this 4. We can have like this. Okay. We cannot have element here. No, this will not be complete binary tree. So first of all, we have to fill this 8, and then we can come on 6. We can keep it like this also. This is also complete binary tree. Okay, if we want to add element, we'll have to add for first for 8, then for the right child of 8, then for the left child of 6, and then for the right child of 6. This is also complete binary tree. If you want to add another element, we have to start from the left side only. Okay, so all the levels will be filled. All the levels will be filled completely. Okay, and the last level will be filled to the left side. Anyone have doubt here? Here, these, I think these all are easy questions. Just horrible thing. Let's say there is a complete binary tree. Let's say it goes like this: 1, 2, 3, okay, 4, 5, 6, 7, 8. Okay, that's it. How many elements are there? There are 8 elements. Okay. How do you represent this tree in an array? Okay, that is a very, like, um very basic question, and we should know. We should know this. Okay. How should we represent this in an array? Let's say we make an array of 8 elements. Okay. Let's say we make an array of 8 elements, and let's say we take this root as the first element. Okay. Let's say we have 8 elements here: 0, 1, 2, 3, 4, 5, 6, 7. Okay. Well, 8 element will not be there. Let's stop it. Okay. So we have 8 elements. We have an array of 8 elements. The first element, let's say it is root. Okay. This is root. Got it? Next to this one, let's say we are filling one by one. So it is 2, it is 3, it is 4, then 5, then 6, then 7. 4, 5, 6, 7. Then we are filling 8. Okay. Let's say we did it. Let's say we did level order traversal. One is saying. Let's assume that. So one by one, we filled it. Like we just did it. Then from left to right, then again left to right, then again left to right. That is the last element. So this is a root element, right? Let's say for this is the 1. How do we know what is the child of 1? This is 1, right? Okay. The left child of 1 is 2 and the right child of 1 is 3. How do we know in this array what is the left child and what is the right child? From tree we know, right? Left child will be on left side and right child we have a pointers. But in rule in array we don't have, right? We just know this 1. How do we know for this 1 where will be the left child and where will the right child? Very easy. Okay, very easy solution. The thing is you just have to do 2 into index of that parent plus 1 for left child. Okay, this is the formula to get the left child. Similarly for right child, we can do 2 into I plus 2. That's it. Okay. So let's say this 1. Okay, this is 1. Okay. So if we calculate through the formula, what it will give? 2 into I. I is what? 0, right? 2 into 0 plus 1 is 1, right? So this will give us the left child of 1. That is 2. Okay. The right child will give 2 into 0, that is 0 plus 2. That is giving 2. So 2 is here. This is the right child. Okay. Let's go for any random values. Let's say you want to get the left and right child of 3. So 3 is here, right? Where is 3? 3 is here. So index is 2. If we put the index in this formula, what it will give? So 2 into 2 is 4 plus 1, which is 5, right? And the right child will be 2 into 2 plus 2, which is 6. So this is 5, this is 6. Can you see? This is left child, this is right child. Is it working, guys? Okay. If you want to get the left and right child of this 4, if you put in 4, the left child will come up as 2 into 4. What is the index of 4? 3. 2 into 3 plus 1 is 7. And the right child will give us as 8. So this 8 is out of the index. We have only 7 index. We don't have 8. So right child does not exist. Left child is 7 index. So this is the left child. Okay. Any doubt here? How do we, for each element, how do we get, is it like clear? Great. What next is there? So you know what, how do we represent an array and a tree in an array? Okay. You know what is complete binary tree? Okay. Okay, let's go there and let's make a heap. So we will be working on maximum heap. Okay, max heap we'll be trying to work. Okay. Yeah, it is for complete binary tree only. In, let's say if it is not a complete binary tree, we can use null values. Okay, that's okay. That you guys know. Now, yeah, let's say it is a, let's say we have a heap 10. Okay, we don't want that. Then we have, let's say 7. Let's say we have 8. Let's say we have 3. Let's say we have 6. Let's say we have let's say we have 8. Let's say we have 5, 1, and let's say 3. Okay, that is it. That is a heap, right? It's a heap. Let's say you want to insert an element. How do we insert it? How do we insert it? Let's say you want to insert, because we cannot just add here. Like let's say you want to insert 9. Okay, 9. Let's say you want to insert 9. We cannot just add 9 here, right? If we add 9 here, it will not be a heap anymore, right? Because this subtree is also does not satisfy that condition. Root should be larger than all the other elements in the subtree, right? Do you agree? Do you guys agree with this? It is not satisfying the condition for heap, right? If we see here, again, it is not satisfying. Why? For this subtree, the root is 7, which is not more than, which is not the largest element. The largest element in this subtree is 9, which is not root. So we cannot add anywhere, right? How do we do it? We cannot add here, we know. Similarly, definitely we cannot add just here. How do we do it then? I'll tell you. This is 9, right? So first, let's say we add it here. Okay. Now what do we do? We want to check, is it smaller than or equal to the root? If it is smaller than root or equal to root, then it is okay. If it is larger than root, then we have to swap it. Okay. So what do you say? If our element is less than, I'm telling it for max heap. Okay, remember, if it is less than or equal to root, then we don't have to do anything. Otherwise, else swap with parent. So what is the parent for this? This condition is false, definitely false, because 9 is not less than and also not equal to root. So it is actually more than, then we have to swap it. So we'll just swap 6 and 9. Okay. The 9 will come here, 6 will come here. Okay. Now we don't have to stop here. We again have to check for this 9. How do we know the parent? I'll tell you one more thing. Do you guys know how to know a parent in a array? Okay, don't worry about array. I'll tell you an array. Just in tree, you know, right? Let's see it here. Then I'll tell you how do we know in array. For each element, how do we get the parent? I'll tell you in just after this. So we swapped it. Why? Because 9 was not less than or not equal to root, right? So we swapped it. Now again, we are checking with parent. Is this 9 less than or equal to parent? Is this condition true or false for this 9? False, right? It is false. So it will again swap with parent. Why? Because this is not satisfying the heap condition. This child should be less than or equal to parent, but it is not. So we have to swap it. 9 will come here and 7 will go here, right? 9 will come here, 7 will go here, right? Now again we are checking it. What do you say this time? Will it satisfy? Yes, that's it, right? That's it. So we have successfully inserted 9. Okay, we have successfully inserted 9. So like this, we have to insert. Okay, let's say now we want to insert something else. Let's just clear it. Okay, let's not remove that. So we don't want to insert 9 now. We have done that. Let's say I want to insert. Okay. Let's say I want to insert 11. Okay. What will happen this time? We will add here 11, right? Because we know it's a complete binary tree. So we'll add it to the left side. We'll add 11 here. We'll check this condition. Is it true or false? Is it 11 less than root or equal to root? False, right? If it is false, we have to swap it with the parent. So we have to put it here. We have to put it here. Okay. So 11 will go here. 7 will come here. Now again, we have to check. Is this satisfying this condition? No. Again, we have to swap. Good, Pragati Bharat, everyone. Very good. So you have to swap 9 here and 11 will go here, right? Now again, we have to check with parent. Now this time, this is the parent. Again, it is not true, right? We have to again swap it. 10 come here, 11 comes here. There is no parent for 11, so we have to stop here. Can you see? We have successfully added 11. Do you got it, guys? This is how we are adding elements. This is an insertion. Okay, I'll write a code for it. Before that, just a quick walkthrough. Let's say if we have one array. Okay, let's say we have an array. Let's make one tree. Let's say we have 10, 9, 7, 8, 5, 4, 3, 2. Okay, if we make an array, it will be like 10, 9, 7, 8, 5, 4, 3, 2. Right? This will be an array, right? Indexing will be 0, 1, 2, 3, 4, 5, 6, 7. Okay. This is from 0 to 7. That means total we have 8 elements. Okay. How do we know the parent of any element? Let's say you want to add one more element. Okay. Let's say you want to add one more element here. It is 700. Let's say you want to add one more element. Let's say it is let it be 9. Let it be 9. Okay. How do we know it? Don't keep it 9. Let's keep it 9 only. So if you're keeping it 9, then we have to make it 8. Okay, this is the array elements 10, 8, 7, and we are adding 9 here. Okay, the new element you want to insert is insert 9. Okay, so we know we have to add one more index here and we have to add a 9 here. Okay, now we need to check it with the parent, right? Is that condition satisfying? So how do we know the parent of 9? Very simple formula. Okay, parent, yes, great Rohan, Akshata. So parent का formula क्या है? Index minus 1 by 2. That is the formula to get the parent. So what is the index here? Index is 8, right? So 8 by 8 minus 1 is 7. Divided by 2 is 7 by 2 is what? 3, right? So this is the index. Okay, this is the index. So we know for this 9, the parent will be 8. Okay, got it? Anyone have doubt here? So we know for this 9, the parent is 8. So we need to compare with it. Is this 9 less than 8 or equal to 8? No, it is actually more than 8. Then we have to swap it. Do you understand, guys? We have to swap this time. Agree with me? Parent is only one. There is no two parents, Mohit. There is no left parent. There is no right parent. There is only one parent. Okay? Yeah. For each left and right node, we have to use the same formula to calculate the parent. There is no different formulas for both. Now for this 9, the parent is 8. We have to swap it because this 9 is not less than or not equal to 8. Agree with me, guys? Do we need to swap it or not? Yeah, great. So we have to swap it. Here will come as 9 and here will go 8. Okay. We'll do the same thing here as well. 9 goes here, 8 comes here, 9 goes here, 8 comes here. Okay. Now we are at this element, right? We are at this element. Again, we'll get the parent using that formula. So now index is 3. 3 minus 1 is 2. 2 by 2 is 1. So now the parent is 1. So 1 is at this index. So now this time the parent is 8. Can you see? Again, we got the parent. For the 9, the parent is 8. Again, we check it. What do you say? Again, we have to swap it, right? We don't have to start it because this is not at its correct position. We have to put it in this correct position. Then only, otherwise it will not be a heap anymore. So we have to again swap it. So we have to swap these two elements. Eight goes here, 9 comes here, 9 comes here, 8 goes here, right? Now the parent of 1 will be what? 1 minus 1 is 0, 0 by 2 is 0. So this is the parent, 0 index, which is 10. Can you see for this 9, the parent is 10. Agree? This time that condition, that if condition satisfied. So it is actually satisfying the condition for a max heap. Now this time the child is actually less than or equal to parent. So we don't have to swap this time. Agree with me, guys? Great. So that's it. We have successfully added 9 here. How do we write the code for it? I'll tell you how to write the code for it. Let me go for it. Should I write it in the lead code playground? Should I write it just a rough code? Okay, then when we'll write the code, then I'll write it. Heapify. Okay. So do you see here? We can do it recursively also. We can do it using while loop also. Using while loop will be much easier. Okay. Yeah. Now, do you see here the top element? The top element of heap will always be the largest element. Okay, will always be the largest. You understand? The top element for each subtree will be the largest. For this subtree, the root element for each subtree will be the largest element of that subtree, right? So we can say it is the highest priority element. So it will be very easy to get the maximum element in a heap. So if this is a heap and we want to know what is the most priority element or what is the largest element, we just need to print the heap. We just need to print the root. That's it. The root will always be the largest element of a heap. Okay. Now your question arises, right? I think you might be having this question. Let's say if we are deleting an element, then what will happen? Let's say you want to delete the topmost element. What will happen then? That's a big question, right? Let's say this is the topmost element, this 10 is there, right? And if we are removing this 10, then what will happen? How the things will change? This root will be, this tree will be without root, right? Because if we are deleting this 10, then we are not having any root. Do you understand my point? Don't have any root. How do we do it then? How do we delete an element? You know how do we insert an element? You guys know, right? You don't have any doubt. How do we insert an element? Our insertion takes only log n time. Okay. Check right child and left child and swap it. That will be complicated. Okay, I'll tell you a very easy solution. Okay. Let's say it goes like this. Array, yaar, we don't have to delete it. We want to delete this root. We can always delete from the root only. We cannot delete any other element. Okay, it would be much more complicated. We want to make a heap where we can insert an element, where we can delete the top element. Okay, and top element will always be largest in max heap. Do you agree with me? And in min heap, the top element will be the minimest. Will be the smallest. So what is the advantage of heap? You might be thinking, right? We put our subtree inside other subtree. We are see this heap will always use a complete binary tree, and this whatever you see here, right? This structure, this itself is a structure. This itself is a kind of tree, heap tree we can call it. Okay, here all the root element for any subtree will be largest or will be smallest based on the max heap or min heap. It's itself a structure. Okay, this heap, we call this kind of tree as heap. Remember this word. Okay, we call this kind of tree as heap, and if we want to represent in an array, we can represent like this. That is the point. Okay, very good, Venkata, very good. We have to replace the root with the smallest element, with the last element. Once we have done that, then we delete the last element. Okay, and then heapify the first element. So you might be thinking, what is heapify? Okay, should I tell you what is heapify? Okay, let's tell you what is heapify. Okay, let's say this is a heap. Okay, this is a max heap. Okay, this is also a array representation for this above tree. Okay, for this above tree, which is a heap, this is an array representation. Okay, now we want to delete root. So you want to delete this first element. How do we do it? I'll tell you how do we do it. We just have to replace it with the last element. What is the last element? Last element is 8. Okay, and the first element is 10. We have to replace them. So 8 comes here, 10 comes here. Okay, similarly we replace it here also. 8 comes here, 10 comes here. Okay, we want to delete it then. This last element is very easy to delete because it is now a leaf element. So there is no child. So we can directly delete it. We just have to erase this pointer and we are deleting that element. So the easiest element to delete in a tree is a leaf node, right? Because we don't have any other child to manage. So let's say we deleted it from here. Okay. Similarly, we just have to decrease the size of this array. This element will be decreased. Now our array has only 8 elements. Okay. Done. We are deleted. Now, but this tree is not a heap anymore, right? After deleting, our tree should remain as a heap. Do you understand? But this tree is no longer a heap. This 8 is not the largest in the subtree. Do you agree? How do we do it then? I'll tell you. Very easy. It can happen in log n time. In log n time, we can make this tree back to a heap. Okay. How do we do it? I'll tell you. This tree, we want to make it back to a heap, and we have this root. We know all subtrees are satisfying the condition. Only this root is not satisfying. Why? Because we are added just now. How do we do it? We just have to compare. We just have to replace this root with the largest element in left child or right child. So what is the largest element in all these three? 9 is there, right? So we have to swap it with the larger element among these three. So this 8 among these three, the largest element is 9. So we have to swap it with 9. Okay. That is what you can do. So we just have to check with the child. So for 8, how can we get the left child and right child? You already know the formula, right? For 8, the left child will be 9 and right child will be 7. You know, right? Using the formula 2 into I plus 1 and 2 into I plus 2. So for 8, we get left child as 9, right child as 7. So we know among these three, this root is actually less than 9. That should not be true, right? We have to swap it with the largest element of the roots. The largest element in these two are 9, which is actually more than 8. So we have to swap with 8, right? So we put it here. 8 will come here, 9 will go there. 9 go there, 8 comes here. Similarly, comes here, okay? Nine goes there, 8 comes here. Now we are at this index, right? Now we are at this index. We again have to check what is the largest element in left child and right child for this 8. For this 8, how do we know the left child and right child? Using the formula, right? 2 into what is the index? 1. 2 into 1, 2 into 1 is 2, plus 1 is 3. 2 into 1 plus 2 is 4. This is 3, this is 4. This is left child, this is right child. We compare it them. So what is the largest in childs? 8 is the largest, right? Is 8 greater than parent? No, it is not greater than parent. It is less than parent. So it is actually satisfying the condition. Now we don't have to swap it any other element. Now this is a heap. Okay. This is a heap. We don't have to switch any other element. This becomes a heap. This was a very easy approach, but I'll tell you for this element. Let's say you want to delete one more element, then it will become complicated. I want to tell you that. Right now it was very easy. But let's say, yeah, 8 and it will come 8. Okay. Now this is a tree. This is a heap again. This tree is a heap again. Now let's say we want to delete another element. So the another element which we can delete is the root element. Now we want to delete this 9. Okay. When we are deleting this 9, again we have to do the same thing. We have to swap it with the last element, and then we have to heapify. So if we are swapping it, in place of 9, what will come? 2 will come, and in place of 2, 9 will come, right? 9 will come here. 2 will come here. Similarly, here will what happen? Same thing will happen. 2 goes here, 9 goes here. Okay. Now, this is the leaf node. We can easily delete it. So let's say we have deleted it. Okay. That is gone. Similarly, we can delete it from the root array also. Okay. So we have only 7 elements. Up to it is clear. We have only 7 elements. We have in the array also, in this heap also. Now, we want to make it back a heap. Okay. This is not a heap anymore. Can you see? It is not a max heap. We want to make it a heap. Are you guys following? How do we make a heap then? What should we do to make it back to a heap? We have to follow the same process. We have to check what is the maximum in left and right child. And we want to check if the maximum of left and right child is actually more than the root, then we have to swap it. So how do we know? This is the root, index is 0. For 0, the left child is 8, right child is 7. So what is the maximum of them? 8 is maximum. We have, is 8 more than our root? Yes, 8 is more than parent. We have to swap it. So this 2 will be swapped with 8. Okay, similarly here. 2 goes here, 8 goes here, 8 goes here, 2 goes here, right? That's done. Now we are, our 2 comes here, right? 2 comes here, down here. So for again, for this one, we have to get the left child and right child. Again, we have to check. So how do we know that what is the left child of 2? Using this formula, we get 2 into 1 plus 2, which is 3, and 2 into 1 plus 2, which is 4. This is the left child. This is the right child. What is the maximum of them? 8 is the maximum, right? Is this 8 more than the parent? Yes, it is more than the parent. Then we have to swap this 2 and 8. Do you agree? Following, na? Huh. We again swapping it with 8. We put 8 here, 2 here, and 8 here, and 2 here, right? Now we are at this location. What is the left child of this and right child of this? So 2 into 3 plus 1 is 7, and 2 into 3 plus 2 is 8. This 7 and 8 both are out of the bound. Okay. This should be less than the size of the array. The last index is 6 only. 7 and 8 both are actually out of the bound of the array. That means we don't have left child also, and we don't have right child also. Okay. That means we don't have to compare anything. That's it. We are done. This is now a heap. Okay. Do you understand now how to heapify a thing? Okay. This is how we have to heapify. So, and don't think we can heapify through root also, root only. No, we can do a heapify for subtrees also. I'll tell you when we'll do heap sort now. Then I'll tell you how do we heapify from we'll start heapifying from here and then here and then here. It like this will go. Right now we just see how do we heapify from root. Okay. Any doubt here, guys? Great. Should we write some codes? We know how to insert an element. We know how to delete an element. Okay. Should we do it then? We know how to insert. Yeah, we know how to insert. We know how to delete. For deleting also we know, right? Let's code it. Let's go for it. Okay. Mhm. If we are coding it right here, will it make any sense? Okay. Don't worry, I'll give you the codes. But I'm thinking, should I code it or should I try you guys to code it? Okay, let's code it. I normally do coding in C++, but for you guys, I'll try to code in Java. There's no issues in that. अरे यार, क्या खोल दिया मैंने? Nice. Leave it, leave it. Let's make a heap, okay? Let's give it a name as heap. What data structures you want here? You want an array list, right? So we'll use an array list to make a heap. Integer, let's say we call it as heap is equal to. If I forget any syntax, let me know, okay? That's it. We have made it. And let's say the size, okay? Let's say the size goes with let's take a size variable. That's it. Okay. Don't need any parameters here. Nothing we need, okay? Yeah. Do we need a maximum size here? We don't need a maximum size here. Let's just give one thing here. Size, let's keep it as 0. It's by default, it is 0 only, I guess, right? Now, we want to make some functions in heap, right? Let's say you want to make a insert function and delete function, okay? So for inserting an function, we need to send one element here. So let's say it won't return anything, okay? Let's keep it, let's give it name as insert heap. We won't have to pass anything. We just have to pass an element, okay? Let's say this element we want to insert in heap, okay? We will write the code later. What other function we want here? We want to delete an element. So we want to delete an element. So for deleting, we don't want to return it, right? We just want to delete it. Or do we want to return the element which we have deleted? No, that does not make any sense. Let's just delete heap. And that's it. We don't have to pass any element. It will always delete the top element, right? Which is the root. We'll code it further. And let's say we want to check what is the maximum element in the heap. Yeah, have I bought a charger or not? Let me see once. Oh, hopefully I have a charger. Great. Just a second, okay? And we want to get the maximum element. So for that will be definitely an int function. So int max heap element. Okay, this will return as a maximum element. Okay, now let's move further. Let's create an object. Let's say I want to create an object of this heap class. How do we do it? Heap. Let's say we call it heap. What name should we give? Let's give some meaningful name. Test heap. Okay, is equal to new heap. Okay, that's it. We have created one object, right? So we are testing heap, right? So we have created one object. Now, initially the size is 0. Okay, if we print it, let's say just print it. System.out.println test heap dot size. Okay, and you have to return here the way it will give some error. Let's run it hotbox. What it does? Heap. Okay, let's make it a public, and of course we have to make it as class name. Okay, we have to all. Yeah, what I have to remove this code. Sorry for that, guys. Class employee. Okay, great. What are we doing? Okay. Test heap is a function name that is not a heap. Heap.size. Guys, you guys have to tell me these things. Yeah, these are all the easy things. What are we missing, bro? Okay. I'm so sorry. Okay. After a long day, I just need a coffee. That's it. Okay, now it is done, right? Can you see we have a heap class, the size is 0. Okay, now let's make it then. We have a size 0. Let's say you want to insert an element. Okay, let's say we call an insert function. Let's say we send here test heap dot insert. Let's say you want to insert 10. Okay, you want to make it a max heap. Okay. Oh, guys, you not able to see it? Can you see it now? Is it visible now? If I do again a spelling mistake, I'm going to get a coffee for me. Okay, you have to take some rest. It's been a long day today as well. Yeah, lot of work. Okay, so test heap dot insert. We are going to insert 10 here. Okay, how do we write the code for it? We know when we have to insert an element. What was the code? How do we insert it? We start from, we have to add it to the last of it. Like, no, let's say we have to add to the last of the array. Okay, let's say this is the array size. Let me go here. So we have to add at the end of the array, right? And then we have to check for the parent. Okay, if it is actually less than okay, we are doing a max heap. If it is more than parent, then we have to swap it, right? Do you understand? Someone is asking test heap dot size. Test heap is an object name. Okay, inside this object there is this this heap is what? This is your array list, right? This is your array. So you have to write like this. Size is what? Yeah, got it now. Now what do we do here? We know we have to get the parent. Okay, so we can write a function to get the parent also. Int parent, we send here index, and this function will give us the parent. Okay, so let's see. Parent, as we know, what is the parent? Anyone knows? Index by 1 divide by 2, right? That's it. Divide by 2. This will give us the parent. Agree, guys? Any doubt here? Okay, now let's say we want to get the left child and right child also. Let's make a instruction for them. Let's say we have an index. We want to get a left child for it. So we had just had to return 2 into I plus 1. Okay, that's it. Sorry, 2 into index actually. This will give us the left child, and similarly for right child, what we can do? Int index you have to send here, and we have to return 2 into index plus 2. Agree, guys? Any doubt here? This is for left child and right child. Now, we want to check what? I'll tell you. We want to first of all calculate what is the parent, and then you have to compare it. If it is actually more than parent, then we have to swap it, right? Okay. And let's say if we have reached to the zero index, for the zero index there will be no parent, right? So we have to make sure that we should not be at zero index. Okay, if we are at zero index, then we don't have to swap it anything. We don't have to check for any parent, because for zero index there will not be any parent. If I ask you what is the parent of root, you will say there is no parent of root, right, guys? Do you understand why do we not need to check for zero index? Okay, right. So while this is a heap, we have to give here index actually. While our index is not equal to 0, this should not be equal to 0. And if this is not 0, and if it is more than parent, we have to swap it, right? And array, what is the name? Heap. Yeah, heap dot get index. If it is more than its parent, what is the parent? Heap dot get. For parent, we need to call this function, right? Heap dot get parent of index. So this will give us the parent. Okay, this will give us the parent. Let's say we have index as 6. Okay, so the parent of 6 will give us what? 6 minus 1 is 5. 5 by 2 is 2. So 2 will be the parent. So at second index, if this element, the child element, is more than parent element, then we have to swap it. Do you agree with me, guys? Do you agree with me? Anyone have any doubt here? If these both conditions are true, that means if we are not at root, and if our child element is more than parent element, then we have to swap it. Agree or no, guys? Swap, right? So let's make a swap function also, and then send here what? Index and parent of index. These two things have to swap. Let's make a swap function. That's a void function that won't be returning anything. It will be just having index and index 1, index 2. Let's give it like that. Index 2. What do we do here? How to swap an element? Any idea? Heap dot parent, where it is? On line number 25. 25. We are going to write now. What is it out? No, 26. 26 is a curly brace. What are you saying? This. Yeah, it should be parent or heap dot parent. No. We are calling this function, right? We are calling this function. Okay, there is no issues in that. No, this is a function we are calling. Okay. Heap dot get, we are getting an element from array list. Which index we want? We want this index. This is giving us the index. That's it. You guys have worked on array list, right? Got it? Okay. So anyone have doubt here? Yeah. Let's store it in a temporary variable here. Int temp will be equal to, we want to swap index 1 index 2, so we should store the index element of index 1. Heap dot get index 1, and then heap dot, how do we set an index? in array list? Can anyone help me? Let's say in index 1 we want to put index 2. How do we set it? Dot set, right? Great. Then you want to set here in index 1 you want to set index 2. Okay, got it? No, not like this. You have to give here heap dot get, right? This will help us, I guess. Am I right? Now similarly we have to do the same thing. Heap dot set index 2 with temp. This will swap the values. Any doubt here, guys? Clear? So we have to swap it, and then what we have to do? Then our index will become parent, right? We have to move to the parent of index. Okay. Yeah, that's it. Now again we'll check if it is not root, and again if this new index is again less than the more than the parent, then again we have to swap it. Okay. Does anyone have any doubt in the insertion of a heap? No, right? Let's say we insert 4 or 5 elements, and let's say what is the top element. Let's say we insert 10. Okay. Yeah, wait just 1 second. Let me copy it properly. Let's say we inserted any other element. Let's say we inserted 3, 5, 1. Let's say 1. Let's say 7, 5. Let's say 32. Okay. Now what do we do? Let's say if we are printing, let's say you want to check what is the first element. What is the root element? System.out.println largest is equal to what will be the largest element always? Anyone? It will be the root, right? And how do we get the root? Through which function? Where is the function? Have we created one function to get the root? Yeah, max heap element, right? This is the function. Max heap element, and I have to call it using test heap. Test heap dot max heap function. Okay. This will give us the largest element, and we have to code it. Which element it should give? It should print what? It should print the first element, right, of array. So it should print heap dot get 0, right? But what will happen if we don't have heap dot get 0? Let's say if we don't have any element in the heap, let's say if heap is empty, then what will happen? It will give error, right? So you have to check it. If heap dot size is equal to 0, then in this case you have to return -1. Okay, let's say we give -1, that means heap is empty, and we can print a message also, heap is empty. Okay. Otherwise, we'll give the first element. So let's say we check it. Let's say is it working or not. Let me just clear it and run it. What we did? Okay, heap test dot insert. Okay, have we given any other name for insert? Okay, insert heap we are given. So we have to give like insert heap, or should we just make it insert here? It will be much easier for us. What do you say, guys? What we have done? Okay, 10 out of bound for length 0. Line number. Okay, Java index 10. Okay, let me just do it. What we have done? Okay, okay. Size. Are we using the size anywhere? No. Okay. Whenever we are inserting. Oh, one mistake we did here. You know what mistake we done here? Anyone wants to tell? No, not that problem. That is not a problem here. Firstly, we have to add this element, you know. We are inserting an element. Let's say we give as element as whatever element, let's call it element, right? So we have to insert it in the end of the array, right? So we have to insert like heap dot add this element. We are not adding it. We forget to add this element, right? Now we are adding it, right? Then we have to shift it. Okay. And how do we get the index? We get the index using size. Okay. So index will be equal to size. Okay. The size initially it is 0. Okay. When we are adding it, it will again be 0 only. But now this time at last we'll increase the size. Okay. Any doubt here? Or we increase it beforehand and then we give it as size -1. Both are same thing. Okay. Both are same thing. Okay. Now this time it should work properly. Let's run it. Yeah. We got the largest element as 34. Can you see this is the top element? Let's say we make it 3. Now our largest will be 32, right? So it's working fine, right? Largest 32. Do you understand, guys? Okay. Yeah, yes, Sanjay, that will also work. So our two functions are ready. We know how to insert an element. We know how to get a max element. Now the only function which is remaining is how to delete heap. Okay. How it is ensuring it is heap. Can you see how we are adding? We are adding one by one, right? And we are always checking this condition. Okay. This is how we are ensuring. When we are doing the insertion, did you not notice how we are doing it? Okay, so we did not had any element beginning, right? In the beginning, it was all empty. So we are adding one by one. Okay, we don't have a random array and we want to make it heap. If we have a random array and then we want to make it a heap, that's a different process. But right now, our array list is empty. We don't have any element. Okay. You want to print a whole list one? Okay, let's do it. It's a good thing. Just for understanding, let's print a whole list. Okay. Uh, let's call a function and then print there only. Okay. Okay. Let's make a function print that will print our list. Mm. Hmm. Can you see? This is 32. Okay. For 32, we have left child and right child, both are smaller. For this 10, left child is 5, right child is 1, both are smaller. For this 23, left child is 3 and right child is 5. Both are smaller, right? Can you see it is a heap? If you try to visualize as a tree, it is a heap. Agree, guys? Cool. Now, we just have to make one more function, which is a delete function. Do you guys want to try to make a delete function? Let's take 5 minutes of time. I want you guys to try making a heap. To delete an element in a heap. You already know, right? I don't want to repeat because if I repeat, it will be very easy. You guys try to remember how to delete an element, make a heap. Try to remember how I told you how do we need a, like, I'll just give you a hint. You have to swap with some element. That is a hint. Write a code right now and send me. Please don't copy from anywhere. That is the most important part of teaching. Whenever I give you some question, you have to try it right away. You don't have to send me your completed code. Maybe you might have done it before, which I'm asking, but you have to code it again right now and send me. Okay. If you have not coded, like, if you're not coded before, try it. Try it. That is how you grow. Okay. Don't send me a code here, man. Okay. Code it on some compiler. Maybe you can use LeetCode Playground. Maybe you can use ide1.com and just send me the link of the URL of the page. I'll see it here. And yeah, and send me personally. Don't send it to everyone. Send me personally. Do you guys agree what I said? Cool. Do it. Just give me 1 minute, okay? Let me just check if someone was calling. Yeah, you want to say something, Rohan? Who is Ikra Banu? I changed my name to Ali. How it is coming Ikra Banu, yeah? In last class also, I used to know like, okay, someone shared me the code. Let me just see the code. What he has written. I'll stop the screen to see the code. Okay. Pseudo code. No, no, no. Don't send a pseudo code. Um, Try to write in Java language. If it is Java language, then let me know if I'll check it. Let me see it just. This is wrong actually. So whatever the swap with na, that should be more than node to swap it. If it is not more than node, then we don't want to swap it. Okay. We will only swap only if it is largest. So first of all, you have to find the largest in left and right, and then we have to check. If it is more than our root, then only we'll swap it. There are so many ways to do it. Okay, someone share the code. Manvith have shared the code. Let me see. Great. You're swiping first of all. No, Manvith, first thing you have to check, okay, the left and right child should be present. If they are not present, and if you're trying to get those elements, then you will get an array of error of out of array index out of bound. So first of all, you have to check your left and right should be present in an array. Understand what I'm trying to say? No problem. Good try. And once you are done, let me know. I'll code it for you. But I really want to see how many of you are coding. Only Manvit tried and Satish tried. Satish, I don't know what. Like he just wrote and that kind of code. No, 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 no. This is not a way to delete. Okay, we have to heapify. It's okay. It's okay. I understand. I think you guys lack some understanding. It's okay, Jagannath. Good try. Pragati have written some code. Let me see. No, we don't have to check 0 here. Okay. Should I help you guys? It will not work on negative elements. Okay, yes. That also you have to make sure. Good try, all of you. Good try, Yash. Most relevant one was yours only. Okay, I'll show you. Do you remember in this we tried to delete a root element which was 9, right? How did we do it? Should I make another tree and tell you the algorithm, or can I directly code? Do you guys remember the algorithm? I'll tell you. Let me just quickly tell the algorithm. Okay. Let's say I want to delete. Okay. So 9, 8, 7, 5, and 4. Okay. This is all other elements. Do you agree, guys? This all other elements. Let's say we want to delete the last element, or sorry, top element. So this is the top element, right? We can only delete the top element only. 9 we want to delete. Okay. Got it? How do we delete it? First of all, we'll swap it with the last element, because deleting this element will keep this uh, tree S without root. That is not possible. So, okay, so we have to first of all swap it with the last element. So basically, what was the first element? 9, right? So 9 goes here and 4 goes here. 4 goes here, 9 goes here, right? Now we can delete this last element easily. Okay. Slowly we can reduce the size of the array and remove the last element. This will also be deleted. Okay. Agree? Now we know after doing it, this root is not the largest. It may not be the largest, right? So what does that shows? That shows that it is not a heap anymore. Now I want to make it a heap. How do we make it a heap? Tell me, guys. How do we make it a heap? We have to compare if it is more than if it is less than any of the child, okay, then we have to swap it with the largest child. So what is the largest child? 8 is the largest child, right? Then we have to swap it with 8. So what we did here? We swapped it with 8. Okay. We moved 4 here, 8 here. Similarly, we swap it with 8. 8 goes here, 4 goes here. 8 goes here, 4 goes here, right? We have to just find a left and right child. You know the formula to find a left child and right child, right? For this 4, the left child was 8 and right child was 7. So we have to find the largest among them and we have to swap it. If it is more than root, we have to swap it. Now we are at here. How do we know what is the left child and right child of this? So index is 1, 2, 3. Left child will be 3, right child will be 4 index, but 4 index is not present, right? So we don't have to bother about it. We only have left index, which is 5. So is it less than 5? Yes. Do you agree? This is less than 5. So again, we have to swap it. 4 and 5 to swap it. Okay. Now again, we are here. There is no left child. There is no right child. And we don't have to do anything. That's it. Now it is a heap. Do you agree? Should I code it? Clear? Okay. What did we need to do here? We need to swap. First of all, we need to swap the first and last element. Okay. And before doing all of these things, okay, before doing all of these things, let's say we don't have any element in the heap, or let's say we have only one element in the heap. In that case, we don't have to do anything, right? Let's say if our heap dot size is actually less than equal to 1. What does that mean? That means we don't have, we may have 0 element or less, 1 element, right? So in both the cases, what we have to do? We can just clear the heap, right? Return null. No, no, no. We can just clear the heap. Do we have any function to clear the array list? Yeah, heap dot clear. I think that should work. Do you are you understanding what I'm trying to say? Good try, Jay. No problem. You're understanding, right? We can just slide here, like, you know. Oh, wait. Let me just handle it, okay? Don't use clear and all. That does not make any sense. If we have 0 size, if heap dot size is equal to 0, in this case, then just return from here. Otherwise, we have to do heap dot remove. We have to give here index, right? 0 index. Okay, that's it. Both cases will happen, and then we have to return from here. We don't want to do anything else. Okay, this is the case. What we'll be doing if our heap is less than 1 size or equal to 1 size. Okay, anyone have doubt here? We don't want to delete it, right? Because we don't have any element or we have only one element. In these two cases, this will handle our code. This code will handle that case, right? Any doubt here, guys? Clear, all of you. Cool. Now, what we got to do? We got to first of all swap the first and last element, right? Now we know we have at least more than one element. So for swapping the first and last element, how do we do it? We can call a swap function and we can send here 0 index and size minus 1 index. Okay, this will swap it first and last. Okay, we have size variable, we don't want to do that. Okay, now what do we do here? We can just delete the last element. Okay, we don't need the last element. The last element will be the root now. So root is already we have swapped it with the last element, so the last element will be root now, and we don't want that, so let's just delete it. How do we delete it? Heap dot remove size minus 1. That's it, we're deleting it. Now just reduce the size also. Okay, got it? Do you agree? Up to anyone have doubt? No doubt. Okay, now we want to heapify. Here comes the heapify. And which element you want to heapify? You want to heapify the 0 index. Okay, now let's make a heapify function. And what does heapify do? As you all know, it will, let's say if we are doing the heapify from 0 index, so for 0 index it will calculate the left child, right child, and it will see whatever is the largest in left and right. If it is larger than our root, so that element, that left child or right child should be root, so we have to swap it with root. Why? Because we are making a max heap, so our root cannot be smaller than left child or right child. If it is smaller, then we have to swap it. Find heapify. Let's say we give it the index. Okay, whatever index we send, it will heapify. So we have to find the largest index, right? Let's consider our index is the largest right now. Okay, let's consider whatever is this element, let's say it is the largest. How do we calculate the left child for it? We have the formula, right? We actually have a function for it. Just send index here, it will give you the left child. So if your left, what is the name, left of index, if it is in range, how do we know if it is in range? If it is less than size. Do you agree? If it is less than size, then it is in range. Do you agree, guys? Okay, if it is less than size, and that element, if it is more than the root parent element, then we can, for now we can take, oh, this may be a larger element, right? So we can take if your heap dot get left of index, if it is greater than heap dot get index. Okay, let's say give it a parent. Okay, it will make more sense. Okay, this is a parent. Do you understand? This will give the left child of parent. Okay, now we are checking. Let me just, can't we just, okay, we cannot increase it, it's okay. So we are checking, where are we? We are checking if our left child of parent is in the range, it's present. We are checking with this condition, we're checking if our left child of parent is present, and if that left child is actually more than parent, then we have to swap it, right? So in that case, we have to make largest. So we can consider that left child is the largest right now, if it is true. So largest is equal to left of parent, right? Now we want to do the exact same thing with the right child. So if this left child is more than parent, then this largest index will store the index of left child. Agree, guys? So now we are assuming that left child is the largest. Now we'll check if we have a right child also. Okay, and that means if it is less than size, that means it is present. And heap dot get the right child. If it is again more than heap dot get largest. Okay, what is largest? You understand largest, right? Largest can be a parent or it can be a left child. Okay, now if it is more than largest, then we have to swap it again. So we just do, we don't need these curly braces here, we can just do largest is equal to, sorry, right of parent. That's it. That's it. Do you agree with me, guys? This largest will store the index of the largest element between root, left child, and right child. Agree? Any doubt here? Cool. If largest is equal to parent, if largest is equal to parent, that means what? That means our root is actually more than left child and right child also, right? So there is no children which are larger than root. In this case, we don't have to swap. We don't have to do anything. We don't need to heapify. It is already a heap. Understand? But if this largest is not equal to parent, that means largest is maybe equal to left child or it may be equal to right child. Okay. In that case, we have to swap it with the largest. We have to swap our parent with largest. Agree, guys? Any doubt here? Anyone who does not agree with this? Anyone who have any doubt here? Cool. I don't think you have doubt, right? Cool. So if we have to check here, just, yeah. So we're checking if our largest is not equal to parent. That means largest element is not parent now. Largest element is maybe right child or right, left child, whatever is the index that is stored here. In that case, you have to swap it. Swap with what? Swap largest with parent. Okay, we are done. We are swapping it. Now again, we have to heapify, right? So after heapifying it, let's say here, when we were doing it, what did we do here? Right? Firstly, we compared this 4 with 8 and 7. So we swapped it with 8, right? So here it comes 8, here it comes 4, it come 8. Now we again have to check for this 4 also, right? If it is actually less than or equal to, if it is less than any of the child, then again we have to heapify, right? For this 4 also you have to check. So you have to call this heapify function now with this index, this 4th index. Okay. Yeah, good. We just have to call the heapify function. Heapify function. What is the, okay, this is not large, this is large. Just let me just correct the spelling here. I have to send here largest. Okay. Got it, guys? Any doubt here? That's it, right? That's it. We are doing it. It's very easy. That's it. Let's see now we run it. Let's see now we run it. So this is the largest element. Let's see if we remove it. Let's say we call test heap dot. What is the function? Heapify. No. What is the function name? Delete heap. Delete heap. Okay. And then we again print it. Now that won't be a largest element. So can you see now 23 is the new root. Okay. Before 32 was largest, then we deleted heap. So 32 got removed. Now we have this many elements in root. Okay. Got it. Can you see this structure also changes? Can you see it is changed now? What does that mean? That means it is heapifying it. Okay, after removing it is heapifying it. So on heapifying it, what happened? 5 came here, right? 5 came here and then it got swapped with the elements and all. So 23 became the new parent and all those things happened. Okay, so this is how it works. Any doubt here, guys? Do you want some rest right now or should we continue? I'll share code with you guys. You can do whatever you want. Okay, you see this link and do whatever you want. I'm sending you link. Anyone can make a doc. You guys can access the link. Let me know if you're not. Only one approach is enough, Gaurav. Okay. Whatever I taught on, that is a standard approach. So you can know that. There is nothing like if you know one approach, you can do other approach also. No one is going to touch that. They just want to see whether you know how heap works or not. Heap is already advanced data structure, so they won't be going into depth. They just want to see whether you know heap, how it works. That's it. So if it is a random array given now, if we have a random array and we want to heapify it now, so it will just take order of n time to heapify it. So make it n heapify it. It will just give order of n time. So in order of 10 time, you can get what is the largest element, what is the second largest element, what is the third largest element. So that won't happen in set. If you want to convert a random array into a set now, and set cannot have duplicate elements also. Okay. And heap can have duplicate elements. Uh, hmm. Guys, just select some approach. Let me see what how do you understand. Yeah, we always delete the root only. In heap, we only have the access to the top element. Okay. For random elements, Vikas, could not understand what is your like for random element, what does that mean? Okay, for random array. I have not taught that yet. I'll tell you how do we, let's say we are given an random array, we want to convert it to a heap. How do we do it? I'll tell you. Okay, don't worry. That is something which I thought I'll tell you tomorrow. Do you want to get some idea? Okay, I'll give an idea. You might can think about it. No, class is up to 11, but that includes a break also. So we can continue for some more time. Okay, yeah. So I see like most of you have understood, you know, what is heap and all. So I'll ask one more thing, okay? No, no, Satish. What I'm thinking now, I have two things. Whether should I give you break completely? Sorry, but should I give you break of half an hour or 20 minutes? Or should I teach till 10:30 and then give you a break? You guys can go and revise like that. So no one said no. That's great. All of you understood. All of mostly said yes. Some of you said no. Matlab maybe actually. Not no one said no. That is great. You guys can see the results. Quickly just give another poll and then we'll start. Okay, so it is very clear. All of you want we should end early. Okay, I think that makes more sense. Yeah, but yeah, you have to sleep and all. Otherwise, it will disturb everything. Okay, I'll just tell you what do we have to do next. Okay. Yeah. You know what is heap? You know how to insert an element, how to delete an element. These things you know, right? Okay. You know the basics of heap. Now, let's say we have a random tree and we want to convert it into a heap. Okay. Let's say we have 10, 25, 9, 11. Okay, let's say this is a random tree. It is not a heap. Okay. Do you agree? Is it a heap, guys? How many of you think it's a heap? It's not a heap, right? It is not a heap. Not a heap. Exactly. What should we do now? How should we convert? So we know we have to heapify, right? We have to heapify. Great, Satish. But if we do heapify from this index, does it make any sense? No, it does not make any sense, right? It does not make any sense. Let's say if it was equal to 26. So it will not swap with any element, right? Why? Because 25 is also less than 26, 9 is also less than 26. But that does not mean that it is a heap, because we have 31 here and all the elements should be less than this 26, right? So this does not implies that it is a heap. So we cannot just heapify from the top. If we are heapifying it, it will not do it if we have 26 here. Do you understand that point, right? Do you understand that point or no? What should we do then? We have to start heapifying from the leaf nodes, okay? Starting from the leaf. So for these leaf nodes, we don't have any childs, so we can't do anything, right? These are all the leaf nodes, we can't do anything, okay? So the first element which have child is 11, right? Understand? This is the first element which have childs. Do you understand or not? Are you agree? This is the first element which have child. So we have to swap it with the largest element. This is the 16 is the largest. We have to swap it. Okay, let's see, make it here, make it here. We are making a max heap, okay? We are not making a min heap. That's it. Now, this is also leaf node. This is also second node which have roots. So we did for it, then we have to do it for it, then we have to do it for it, and then we have to do it for it, then we have to do it for it. So in this way, we have to heapify. So this is the second node which have child. So we swap it. So it should be swapped with 7, right? Because 7 is the largest element. Do you agree up to here, guys? Now this again you have to swap it. This is the third element which have some childrens. So you have to swap it with 31. 31 goes here, 9 goes below. This is the next element. We have to heapify it. When we are heapifying it, what will happen? 25 will not be swapped with anyone. Do you agree, guys? You agree, right? 25 will not be swapped with anyone because left child and right child both are smaller than it. Okay. Did you got it? Why we are not swapping with any child? Cool. Then we have to check for 10. For 10, we have to swap it with which one? We have to swap it with larger element. So this is 31 is the largest. 31 goes up, 10 goes down. 31 goes here, 10 goes here. Now again, you have to check, is 10, is there any element which is more than 10? Yes, this 21 is more than 10. So we have to swap it with the large element. 10 goes here, 21 goes here. Now there is no child for 10. So can you see now this tree is a heap? Now it is a heap. Anyone disagree? It's easy, right? It's easy, right? We just have to figure out what is the first element which have childrens. Okay, I'll tell you. I'll just give you the array implementation for it. Okay. Let's say, let's go back to the original element which was like that. Okay. So this 10 is the first element. Okay. Then 25, then 9, then 2, 11, 21, 31, 5, 7, 5, and 16, right? Why are you calling me boss, bro? You can call me. No, don't worry. Don't call me boss and all. Okay, just try to be a bit serious in the class. Okay, it's not a joke going on. You can call me with my name if you want. You can call me sir also if you want. Don't just write anything whatever you want in the chat box. Okay, just try to maintain some discipline in the class if it is possible. Okay, now don't mind. Okay, I'm just telling to everyone. You guys are very good students. I understand, and I feel good in teaching you. I feel like I'm very like no. You are as very sincere. You are very active in the chat box. I see. Yeah, and so it's just that something. I just want to keep class like this. So I'm really sorry if it like no if I offered to do it. Just uh, a normal point. If I like no, whenever I feel something which is not going right, I'll just point out like no immediately. That is what I do normally. Okay. Uh, where are we? Where are we? You want to know why we are not doing with root, right? So let's say if we had here 26. Okay, we want to heapify it. Let's say you want to start from root. So what will happen in the first step only? We don't have any child which is more than 26, right? So we won't even heapify it. Do you understand? We won't do it. We will just stop here. But that's not true, right? It is not a heap. We have 31 here, which is more than it. Okay, that is why we want to do it. Understand? Okay, good. Now, but here it is 10, not 26. So this, let's say indexing as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. How do we find out which is the first element which have childrens? How do we find out? How do we know? So leaf elements will be at the last, right? How do we know which is the first element that does not that is not a leaf element and that has some child? How do we know it? Anyone have any idea? No, not middle element of the list. Middle element can be two now. Let's say if we have odd number of element, then middle will be something else. If it is even, I want a formula so that it should give only one element. So normally in this case, this is the like this 11 is the first element, right? Can you see after 11, whatever elements are there, these all are leaf, right? So we want to get this 11. How do we get it? Parent of last element. No, 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 no. That is not possible. One thing you get, that is actually who said that? Pritam. That's actually correct. That's actually correct. Okay. But how do we know the last element is a left child or a right child? We don't know, right? We don't know this is a left child or right child. So do you understand? So we have to make a common formula so that it works for left child also and right child also. Do you understand, Pritam? You said the right thing, but you just have to go in that direction and filter it. Give me one formula. Okay, you said last element. Okay, Akshata said that. Good, Akshata. Very nice. I'm sorry. Huh? She said keep parent of last element. Okay. Last element minus 1 by 2. Pritam, do you agree with this? Last element is 10 index, right? So 10 minus 1 by 2 is what? 10 minus 1 is 9. 9 by 2 is fourth index. Okay. But let's say it will not work in one case, Pritam. I'll tell you which case. Let's say we don't have this 16. Okay. Let's say we don't have. Now what will happen? Your formula will give what? 9 minus 1 by 2 will give a, no, wait. Element is 9. Okay. 9 is the last element. 9 minus 1 is 8. 8 by 2 will give 4. Okay. If we go here, it will come here. Okay. But if we have, let me see if it for all the cases. Let's say if we had like that. Okay. Great. Great. Yeah, I think this will work for all the cases. Yeah, this will work for all the cases, I guess. Okay, great. Now, so for one element, we don't have to find it. Okay. If we have only one element, there will not be any parent. Matlab, there will not be any element which have childrens. Okay. That single element will be a leaf element only. Okay. So the formula which he gave is last element, the index of last element. Let's say it is 10 minus. We can just write a random, not like that formula. So last element minus 1 by 2, right? So if we have the 16, the index is 10. So 10 minus 1 is 9. 9 by 2 is 4. So this fourth index, this will be your first element which have childrens. Okay. So we have to start heapifying from here. Understand, guys? So first heapify for this one. Okay. Call the heapify function from this 11, then call with 2, then call with 9, then call with 25, and then call with 10. In this way, your random array will convert into a heap. That is the way. That is a normal basic way. Okay. So you already have the code for heapifying, right? This is the code for heapifying. Okay. So you just have to call this code, call this function by finding the first root. Let's say the first element, which is non-leaf, is 11. We found it. So call it, first of all, call with the index of 11, then call with, where is it? Yeah, first call with this 4 index, then call with third, then 2, then 1, then 0. After doing it, it will be a heap. Anyone have any doubt here? Great. Very great, guys. Good. Do you want to try coding it? I think it's very easy. Whatever I told, you just have to put it into code. That's it. Do you want to try coding it? Do you want to try or no? Let me just see how many of you try to want to code it. Why no? Why, bro? Why you don't want to code? Exactly. Code it. I have shared you the code, right? Change in my code and try to see does it actually works. Make a random array list. Okay. And then use my heapify function. I will prefer write your own heapify function and then try to make that array into a heap. Do you want to try it? This is how you will learn, bro. I told you now in the first class. That means on yesterday also I told you you'll have to try a lot. You have to you will feel like these structures are very complicated. Sometimes you will feel it is very easy by seeing, but really when you will sit for coding, you will understand, oh, these points are like that, and it will help you to understand more. You are feeling right now you know everything about heap, but that is not true. When you will code it now, then you will understand more. This is what I want. Please code it. It's a request for you guys. Okay. Jagannath, Vikas, everyone, please. Pritam, Akshata, Satish, Sanjay, Yash, everyone. Please, guys. Yeah, Umesh. Okay, Pratima is also active. Got it. Bharat has left the meet. It's okay. Quickly try to complete it. Okay. I'll review the code. Okay. That's it. Give me 5 minutes. I'm coming from restroom. Okay. I'll just get a copy for me as well. If you want, you can get it. Some water if you want. Okay. Just coming in 5 minutes. So please, guys, code it. Those who don't want water or something, just code it. I'm just coming in 2 minutes. Anyone wants to share the code? That was straightforward, right? Could anyone try it? Okay, take some more time, no problem. Okay, sorry guys. Mhm. Okay, Manvit share the code. Let me see. Not good. Last not good. 0. Okay. There is one mistake here. It's okay. I'll identify what is the mistake. Because is doing what? Manvit, there is one mistake in your code. I'll highlight it. Let me just see the others code. Happify all. Hmm, that makes sense. We have to apify Vikas from last index only. You don't have to subtract one from it. Jagannath, let me see the code. Yeah, similar. Array dot length may not give you the first element. You know, let's say in this tree, if we have, let's say for the 16, array length is what? 11, right? 11 minus 1 is 10. 10 by 2 is 5. But 5 is not the child. You know, can you see here? 4 is child. So array dot length may not be able to give you the right child. Okay, Jagannath? Let me see your code. Heap size by 2 minus 1. If it is 11 by 2 is 5. 5 minus 1 is 4. If it is 10, 10 by 2 is 5. Okay, yeah, it will work. Now, let me see this code. Yeah. Uh-huh. Mhm. Yeah, that makes sense. Good. No. This will not work. I'll tell you why. This can stuck in some points. Okay, I'll tell you where to be stuck. Yeah, I'll show you. Just a highlight for you guys so that um, let me make it 5. Okay. Let's say we have 6 here. Let's say we have 8 here. Okay. Mm-hmm. No. That I'm not saying. That will work. I'm showing something. You guys have did one mistake. I'm showing something. Okay. So in this case, what do you understand, guys? Let's say we have 4 here, we have 6 here. Let's say we want to epify it. So what you guys are doing now, I have seen you guys. You are first checking with left child, and if it is if left child is more than parent, then you are swiping it. So if you are swiping it, 5 will come here, 6 will go there, right? Then again you are checking with right child, so it will get again swapped. 8 will come here, 6 will come here, right? So can you see, you're not just actually changing your largest element comes at root, that is correct, but you're also swiping these two elements. That you should not do. That is wrong, okay? Because now you have to happify both cases, okay? Both the cases. Let's say instead of 7, instead of 6, let's say it was 7 now. So you have to happify this also and this also, because this 5 is actually less than 6. That is why we have to find out the largest and then check that if that is actually more than our root, then we have to swap it that. We don't have to swap with all the largest elements. Did you got the mistake what you guys are doing? Just a highlight for you guys. That is why I'm saying you might understand ki you understood the heap and it is very easy. But when you will code it now, then you will find out ki you are doing mistakes and then you will learn. Did you understood what I'm trying to say? Let me know, guys. Is there any doubt? Did you got it what I'm trying to say? I think Rohan got it. Anyone else? Okay, great. Okay, yeah. So it's just a very easy code. Just find a parent. Just use that formula. Okay? That formula you can use. Just send last index in parent of heap dot size -1. This will give you the parent, and that will be your last. That will be the first element. Okay, that will give the index of first element that have some child, and then we can just run a loop from I is equal to index. Sorry. And I greater than equal to 0, I minus minus, and then again always call heapify function with I. Okay. After running this for loop, your array will become heapify. Okay. Any doubt here, guys? Got it, right? I wanted to tell you heap sort also. Should I share it or should I not share it? Heap sort. That is the last topic. I like, just trust me. This is the last topic. It won't take much time. Okay. It won't take much time. I'll quickly tell it. Let's do it on this array. Okay. This array only. So after heapifying, what it will look like? Any idea, guys? Yes, exactly, Ron. How do we do it? Any idea? After heapifying it, what it will become? First of all, we'll heapifying this 11. Okay. How do we do it? The right child and left child of the element is what? 9 and 9 and 10, right? I'll show you. Firstly, we have for heap sort, there are two steps. First steps is heapify a random array. This is a random array we want to sort, right? First heapify whatever we learned here. Okay, whatever we learned here just now. Okay, using that we have to heapify. So we have to start from the first non-leaf element, that is 11, then heapify it. So after heapifying it, what it will become? Let's just heapify it here. So first it will become 16, it will become 11, right? Then we'll heapify this, it will become 7, it will become 2. Okay, then we heapify this 9, 9 will become 31, this will become 9. We heapify 25, 25, what is it? It is 5 only, so it won't get heapify with anything. Then we try to heapify this 10, 10 will become 31, this will come here, then it will give 21 and it will come here, right? So after heapifying, the root will be 31. Okay, then 25, then 21, then 7, then 16, then 10, then 9, 5, 2, 5, 11, 5, 2, 5, 11. That's it, right? Anything which we are missing? This is what will be the new array looks like. It's a heap. Do you agree, guys? It's now a heap. So we are done with the first step. We have converted that random array into a heap. Yes or no, guys? Now we want to the largest element. If it is a heap, the largest element will always be at root. Okay, this is the largest element. Now what do we do? If we are uh, trying to sort in ascending order, so this largest element should come to smallest element. That means it should come to last index. Okay, so we can do one thing: 11 here, 31 here, right? Okay, so this is at its right position. Do you understand? If it is the largest element, it should come at the last. So this is already at its right position. We have swapped it. So now we don't have to do anything with it, right, guys? Do you agree? This came to its right position. Now we don't have to do anything. We don't want to touch it. Now what do we do? Now we want to heapify. This 11 is not at the right index. After swapping it with last index, this is no longer a heap. So we want to make it back a heap. And you know, there is only one element which is not a heap, this 11 element that is actually disturbing it. And we also know that this 31, we don't have to test it now. We are reducing our array. Okay, so this element will be removed from array. Okay, so now only we have to heapify from this till this index. Okay, this index we won't include. Okay, otherwise this will come at the top. Do you understand? This will come at the top if we heapify it. Do you know now why it will come at top? Because this is the largest element, but we don't want it. We will ignore it because this has came to its right position in the sorted array. It will come at in this index only. So it is already present there. We don't want to touch it. Now we will heapify it. So let's say if we are heapifying it, 11 will be swapped with 25. So 25 comes here, 11 comes here. Then again 11 will be tested with what? So I'll show you in 3 also. So firstly, 11 comes here and 31 comes here. Okay. Now we don't want to check it. We are deleting it from the heap. Okay, we are deleting it. Now we want to heapify it. If we are heapifying it, it will be swapped with 25 first. Okay, so 11 comes here, 25 goes here. Now it will be swapped with 16. Okay, 16 goes here, 11 goes here. 11 goes here. So let's swap it here also. Okay, yeah, that's all. We are doing heapify for n times. So now what will happen after 11 is again comparing with is it more than 5? Yes, it is more than 5. There is no children which is more than 11. So it is done. It is back into a heap. Now this structure is again a heap. Do you understand? Okay, do you understand, guys, here? Cool. Now what do we do here? We are done with it. We have a heap here. Now again, if you will see this tree again, the top element is again the largest in this root. Okay, this will actually the second largest because largest we have here that we have removed from the heap. So whatever is the new root, that will be the largest element. Do you agree? This is again the largest. So again we have to swap it with the last element. So this will go where? This will go at 5th index and this will come here. So we just, if we do it, this is last element, right? Okay. So 5 comes here and 25 goes here. Okay. Now our array reduced to this and we want to do same thing here also. 25 goes here and 5 goes here. And we want to remove it from our array. So we want to remove it from our 3 also. Okay, so now we have one more element reduced. So these two elements are at their correct position. We don't want to check there. Again we do the AP5 for 5 also. Then again we swap it. This time we'll one by one we'll keep doing it, and one by one we'll be getting the largest element. Now this time 21 will come to the top, right? Then again we'll put 21 to the last. Like this we'll go. Do you guys understand this? Yeah, that's exactly. Good, great. Don't try to make a new array. We don't need a new array here. We can do it in place only. Okay. What we are doing here, we are doing a heapify operation again and again, and each time we are reducing the size. Okay. That's all. Let's say we have one sorted array. Let's say we take one sorted array. 1, 2, 3. Let's make it like this. 1, 2, 3, 4, 5. Let's not, we don't know whether it is a heap or not. Let's take it just in sorted array. So if this array is sorted, what do you think? Is it a min heap? Heapify an array will take, and if you heapifying one element, it will take log n time. If you are heapifying n element, so n into log n will be n log n. Okay. So to heap sort algorithm takes n log n time. Okay. Got it? What do you think, guys? Is it a min heap? Obviously it will be a min heap. If array is sorted, it will always be a min heap. Okay, there is no doubt in it. So this is sorting also. This we are doing it not for making a min heap, but like accidentally we are making a min heap also. But we are doing these operations to make array sorted. Okay, the primary purpose of doing these operations is to make the array sorted, but indirectly we are making a min heap also. Okay, now this is what a max heap is, right? Now you guys know how do we insert in max heap, how do we delete an element in max heap, how do we sort in ascending order using a max heap. So if you want to do the same operations in min heap, can you guys do it? If you want to remove an element from min heap, if you want to add an element to a min heap, if you want to sort an array into let's say descending order, so we can do the exact same operation for min heap, right? Okay, you guys can try it out today. Maybe it will help you. Anyone have any doubt? See, when you see a heap, you always try to see it from the top side. Okay, because so you can only see the root. Okay, you can only see the root. So you want to delete the root only. Okay, that is what you see. Let's say you have a stack. So that is a data structure. That stack is a data structure. Otherwise, you can take an array now. In array you have access to all the elements, but you are taking a stack. Why? Because you want to show you can only pop from the top. Nothing else you can do. It's not like you cannot do it. It's just that we want to keep in mind that it's a heap. Okay, we want to like just these all are some standard data structures which has their own purpose. That is why uh, normally we don't need to delete from a middle of a heap. If we want to delete it, there is a way. There is a way to delete it from the middle. Let's say we have a root and we want to delete it. How do we? I'll just verbally tell it. Let's say we have a root, we have a tree, and we want to delete some element. Okay, let's say we have the index of that element. Okay, in tree we don't have access to middle elements, right? We just have access to root. So in tree that is not possible. We have only parent to delete. But let's say we are representing a heap into an array and we have an index, some middle index, we want to delete it. How do we delete it? So I'll tell you how do we delete it. Okay. Okay, let me tell you. Let me think. How should I tell you? Okay. Got it. So for deleting an element, what we got to do? For deleting an element, we need to put it to the root, right? Then only we can delete it. That is what we know. We only know how to delete from a root. And let's say we want to delete some element from somewhere middle, right? So we need to, let's say it is a max heap. So let's say that element is, I'll tell you what is that element. I'll just quickly, it's a good question, so I'll just highlight it. Because you guys were so much in doubt, we normally don't delete. So just remember, whenever you're making a heap, you don't have to delete any middle element, but you're asking this question again and again, so I'll just highlight it. Let's say you have 10. It's a max heap, right? So it will be 5. Let's say 7. Let's say 4, 3, 6, 5. Okay, let's say we want to delete. Let's say we have some other element 2, 3. Let's say we want to delete this 6. Okay. Oh, don't delete this 6. Let's say 4. No. Now we want to delete this 6. How do we delete it? We have to first of all replace it with what element? We have to replace it with, any idea, guys? Max child? Great one, very good. We have to replace it with max child. Okay. No. We have to replace it max child. So here there is no 6 anymore. Here it is max heap. Okay. Understand? Now what do we do? Here's the maximum integer element. This is the maximum integer element. Maximum integer element is like 2 to the power 31 or 32. Right? Now what do we do? Any idea? Check parent value, hippify. I just left, right. Hmm. Okay, you guys are saying we want to move it to the last element. Okay, that makes sense. That makes sense. So if we want to move it to a last element, then we don't want to convert it into a max, right? Then we have to convert it to a minimum element. Understand? If let's say if it is a minimum element, then it is easy to move it to the last. Do you understand? If we are having a minimum element, then only we can move it to the last, right? So now, if we are moving it to the last, then what will happen? I think this will be swapped with 4, right? So 4 will come here and this will go to the in place of 4. This 4 will come here and this minimum will come here. Understand? To it is clear. So this element which we need to delete, is it here, right? What do we do now? No. Hmm. Okay. If I tell you, you will guys can get confused. Okay. Yes, we have to amplify, but at right time. Mhm. No. If we are swapping it to the last element, then it can make it an non-heap, So we have to keep it as a heap only. We don't want to make it not heap. So okay, we have to keep it as a heap, and then we have to think an algorithm. It was minimum element. It got swapped with 4. It is a heap right now. Okay. That cannot go top. Okay. If we are swapping it with root, okay. If we swap it with root comes there, it goes there. Okay. Got it. I got it. What we have to do. Okay. Okay, it's very easy, but don't get confused. I'll tell you what we have to do. Just give me 1 minute. Otherwise, let me just think how to tell you guys. Okay. Okay. See, let me go back here. What we were doing initially, that was right. Okay. We have 5. Let's say we have 4 here. Okay. We have to first convert it into a maximum element. Okay. We converted into a maximum element. Got it? This you guys understand? Is there any doubt here? No doubt, right? Now we want to do the same operation which we did last time. So if we are doing that operation, we call it decrease key. So what we did, we have to check it with the parent, right? We have to check it with the parent. We have to check if it is less than parent or not. So if it is more than parent, then it should be top on. Like no, if it is more than parent, then we should swap it, right? This is what we do. So if we're doing it, so this is actually more than parent. So parent of 6 is parent of this maximum element is 7, which is less than maximum. So we have to swap it. So 7 goes here and that goes there. Okay. 7 comes here. This max element goes here. Okay. Got it? Now again, we check it with parent. Now this time what will happen? Again, it will get swapped, right? Why? Because this is actually more than parent. So you remember this operation, now? This is exactly same operation. Where is that operation? Yeah, this insertion operation. So we are inserting. Okay. What we are doing, we are checking with the parent. And if it is more than parent, then we are swapping it. That is what we are doing here. Okay. Are you getting, guys? We again have to swap it with 10 also. Why? Because this is more than parent. So 10 will come here and this will go there. Okay. So maximum will come here and 10 will go here. Okay. Up to here, is it clear, guys? How this element, this maximum element, where was 6, we convert into maximum, came to the top. Okay. And it is still a heap. Do you agree with me, guys? This is still a heap. Any doubt here, guys? Up to here, do you guys understand what we are doing here? Okay, Vikas, what dot do you have? We have to convert into a maximum element and do that insertion operation. Okay. For that insertion option, okay, great. We just have to move it forward, what we did there. Now what do we do here? Yeah, doubt. Rohan, tell me what is doubt. What are you writing? So just copy pasting your previous question. I could not understand. Can you just tell it in some other way? So need to make 6 is equal to root plus 1. And then delete root after heapify. Root is equal to 6 is equal to root plus 1. No. Root plus 1, I don't understand what you mean by root plus 1. Okay, so first of all, guys, up to here, what we did here, firstly, we converted that element into a maximum element and we did decrease operation, right? We just compared it with the parent. If it is more than parent, then we are swapping it. So definitely this maximum element will come to the top. After doing it, this will always come to the top. Do you agree with me, guys? Do you agree with me, guys? Up to here, right? Now, this is the same operation which we're doing. We just have to delete element. We just had to call this function. That function is delete heap. It will do what? First of all, it will swap this max element with last element. So max element will come here and last element, this is 4, will come here. Okay. And then it will delete this element. So this element will be deleted. Okay. Now what do we do? This here it is 4, right? We have got 4 here. Now we just have to call the heapify with this 4. So if we call heapify, what will come? It will first of all swap with 10. So 10 goes there. 4 goes here. Then it will swap with 7. So 7 goes there. 4 goes here. Then, oh, sorry. 7 goes there and 4 goes here. Just 1 second. Then again, it will swap with 5. Okay. So 5 goes there, 4 goes here. Understand? It is still a heap and we have deleted that 6th element. Did you guys got it? Great. If you're suggesting the same thing, that's great. Now, yeah, thank you, Akshita and Vikas. Great. So that is how we have to do it. I'll repeat it again. I think there was some confusion because initially we were removing the algorithm. So I'll just repeat it again. Where I'm going. Let's say we have an element like this, 10, 7, 9, 5, 4, 3, 6, like that. Okay. Let's say we have some element. 1, 2, 2, 2, 3, 2. Okay. Let's say we want to delete this. Okay. What do we do here? If we have to, no, you can write in the chat box. You don't have to unmute yourself. So what do we do here? First of all, we have this 3. First of all, we have to make it as maximum element. So if we make it as maximum, then what do? We have to swap it. We have to check, okay, with the parent node. If it is more than parent, it will be swapped. So definitely this maximum element will always be more than parent. So we are deleting 3 right now, okay? So we have to swap it. What do we do here? Maximum goes here and what will the element? 9 were here there. So 9 goes here. 9 comes here, maximum goes here. Again, same thing we'll do, okay? 10 goes there and like it will be swapped, okay? It will be swapped with 10. 10 goes here and max goes here, okay? Now what do? This came to the top. The element which we wanted to delete, that is at the top now. Now we want to swap it with the last element. Last element is 2, okay? 2. So 2 goes here and max goes here. Now we can easily delete it because it is at leaf. So we can easily delete it. It is like this. We deleted it. Now what do? We just have to heapify it. If we are heapifying it, what will happen? It will first of all swap with 10. Okay. So 10 goes here, 2 goes here. Then again it will swap with 9. 2 goes here, 9 goes here. It will swap with 3 again. Okay. Understand? It is still a heap and we have deleted it. Got it? No, we cannot directly swap it. That is not possible. Okay. That won't work. If we are swapping it with the last element, that won't work. That may not work. Okay. Let me give you an example. My God, time is very less. I think you should give some time by yourself. Yeah. If I'll highlight everything, it will be a spoon feeding to you guys. Yeah. It is same as we swapping with root. We just have to put that element to the root and then we have to delete the root. Deleting root, you guys already know, right? To delete a root, what do we need to do? We just need to swap it with the last element and easily delete it. Same thing what to do here. Okay. Shall we continue tomorrow now, guys? I had a big day and I'm just feeling now very tired. Great. Good night, guys. Take care, everyone. Okay, thanks a lot for guys attending the class, and it's been 11, almost 11, and you guys were here. That's great too. Like, no, see. Thank you. Thanks a lot, guys. Good night, Mohit, Shoaib. Thanks, Shoaib. Good night, Akshata, Gaurang. Thank you, Gaurang. Thanks, Sanjay. Good night, Pratima. Good night, Jagannath. Thank you, Sanjay. Thanks a lot. Good night, Vikas. Take care, guys. Good night, Rohan, Mohit, and Manvit.